our next talk. This will be from Cadence Design Systems. Our speaker is Pulin Desai. He's spoken at our conferences before, so some of you may be familiar with Pulin. He's the director of the Vision and AI product marketing. He's a group director in the Tensilica IP group at Cadence. He has more than 20 years of experience prior to that in DSP and microprocessors and graphics. So he's a very experienced, knowledgeable guy. And I'm looking forward to Pulin talking to us about Cadence's Edge AI IP solutions. So welcome, Pulin.
Thanks, Mike, for the introduction. And as Mike says, my name is Pulin Desai. I'm from Tensilica IP group at Cadence. And today I'll be talking about our Edge AI processor IP solution for broad market. So Tensilica has been in business with processor and DSP for a long time. We have our customers are shipping over 7 billion processor annually. We are number one in terms of DSP IP licensing revenue. We are number one in Vision DSP IP and our audio HiFi DSP IP. 19 out of the top 20 semiconductor vendors use Tensilica IP. We have over 300 worldwide licensee, and this number is increasing every year. And one of the most important is ecosystem partners. So we have over 200 ecosystem partners who develop software on our IP. So today we'll be talking about voice AI and vision AI. I'm sure most of you are familiar with this, that voice AI is already used today in the smartwatch, mobile, smart speaker, headphones, and hearable. And vision AI is used already in the mobile platform, AR, VR, smart surveillance, and autonomous vehicle. So when we take a look at an AI inferencing on the edge, usually you will have this kind of a data flow where there is a sensing device that is sensing the outside world, for the vision, maybe an image sensor, radar, or LiDAR sensor, or a voice sensor, microphone. Then there's always going to be some kind of a pre or a post processing. So there's some pre-processing before you provide it to the inference block. And then post-processing depending upon what you're trying to do, or the network itself may have a post-processing. So any sensing application always has some pre and a post-processing. So while trying to solve this problem of inference on the edge, one need to solve the whole data path. So let's talk about an example of a smart speaker. So, as you said, smart speaker. So speaker has obviously the speakers. For input, it has a microphone. So in this application, one would need to run voice processing, some kind of audio processing, and there is always going to be some kind of an AI processing, it being a smart speaker. So in terms of AI workload, you might have a keyword and command recognizer, voice enhancements, noise suppression. In terms of audio, you might have some kind of EQ, MP3 decoder, a speech decoder, or for the voice, active echo cancellation. So in this example of a smart speaker, one would need to process, as we said, audio decoding, AI, and also voice processing. So any solution that's offered in this kind of a smart speaker would have to be a general purpose solution that can solve all three of this workload. The similar way, if we take a look at a camera pipeline, in a typical camera pipeline, you might have a Bayer sensor, and then there might be some pre-processing for the Bayer data that comes from the Bayer sensor. And after the Bayer ISP, once you are in the YUV domain, you might do some kind of a pre-processing in a classic noise reduction in a high dynamic range, or preparing the data before the AI processing, like image pyramid. And then there is an AI processing depending upon the specific network you are doing. And then there is a post-processing Again, it might be something like NMS, or you might be doing some deblurring or some kind of a bilinear interpolation. So looking at a camera pipeline, also you would have some kind of a pre and a post processing before while you're doing an AI inferencing on the edge. So here I'm looking at a couple of examples of edge AI application with vision, which is a mix of vision and AI. So if you are doing a face detection, you get the full image, and then you might end up doing what is called a multi-scale pyramid to scale the image, and that is a classic computer vision application. And then you will have an AI operation to do a face detection. Then let's say if you're trying to do an HDR application, and you might run an AI to do a scene detection. And then depending upon type of scene, you might have different HDR algorithms, and that is your classic computer vision operation that you would run. So if you're doing a bokeh with a single camera, you might do a segmentation with AI, so run a segmentation neural network segment out, and then depending upon which part you want to focus on, you might do blurring and deblurring, which is a classical vision and AI vision operation. So all these use cases, you still have a mix of vision and AI operation, and at the end, trying to do a edge AI operation on the edge with a vision, you need both vision and AI processing. Let's go a little bit deeper and take a look at a specific neural network example. I've chosen here MTCNN. It's a face detection neural network. In MTCNN, you will usually have three separate net, P, O, and R. And a glue processing is inserted between the nets to perform end-to-end face detection. So if you want to speed up this network, the bottleneck may be coming from the glue processing. And in order to improve the glue processing performance, a high performance DSP targeted at the vision application is something that is required. Now, if you take a look at a hypothetical speedup with a convolution accelerator. So convolutions are common, as we all know, in AI, which are multiplier accumulator heavy. So those are a typical target for acceleration with hardware. But depending upon network, just speeding up the convolution may not achieve the performance you are looking at. Some networks will achieve modest speed up, and some networks will achieve a much higher speed up. That all depends on what percentage of the cycle are being spent on other layers other than convolution. So we look at an example of different networks. So on this graph, on the horizontal axis, you are looking at a timeline of when some of these networks were deployed. And on the vertical axis, you are looking at the percentage of cycle spent in layers other than convolution. So you would see that depending upon the network, you might end up spending 20%, or in some cases as high as 80% of the cycle. Those are non-convolution layer. So here again, a high performance DSP targeted neural network application needs to be there to keep up with this evolving requirement. So till now, what we have talked about, that AI inferencing is not just a convolution problem, and it depends on the network. You will have a different workload. We also talked about before and after in inferencing, that there's always going to be a pre and a post processing blocks. And we also talked about that there is, vision AI and the voice AI, and then that means you will need a domain-specific solution to offer for this edge AI application. So let's dive into some of the Tensilica product offerings. Tensilica, we offer two type of edge AI IP. One are highly flexible, multi-use, highly programmable DSPs, and DNA, Deep Neural Network Accelerator, which is scalable AI processor that offers best-in-class power and performance. So on the highly programmable, flexible DSP side, we have Vision DSPs and HiFi DSPs. Our Vision DSP, Vision P6 and Q7 are targeted at Vision plus AI applications. So the main purpose of this DSPs is to do the vision processing, but then it can also offer up to 512 Mac or one top type of AI performance on this Vision DSP. The similar way, HiFi DSP, it can do the voice processing, audio decoding, and also can do some level of AI processing. The thing that we talked about typically like a wake-up word type of a processing. And when we come to the DNA, that as I said, the deep neural network accelerator, it is focused on AI accelerator. So over here, you are getting the best in class in terms of power and performance. We'll talk more about each of these things in next few slides. So our HiFi DSP is a leading IP for audio, speech, and machine learning application. It enables our customers to train and seamlessly deploy the machine learning application on HiFi using TensorFlow Lite for microcontroller. HiFi DSP has over 160 software partners. They are that can provide the software solution, and we also offer Extensa audio framework to accelerate integration of machine learning and traditional audio workload, and thus reduce time to market. Vision DSP. So Vision DSP is, we have two product, Vision P6 and Q7. Those are offered for Vision plus AI at the edge. Vision DSPs offer vision acceleration, AI acceleration, high data throughput, and library tools. In terms of the vision acceleration, these are 512-bit SIMD machine, 5-slot wheel IW, highly programmable, 8-bit, 16-bit, 32-bit integer processing, and single and half precision floating point support. So very vast and diverse data type support. In terms of AI acceleration, 256 and 512 8-bit multiplier accumulator, also half precision support. And in Vision, you're moving a lot of data, so you have a 1024-bit memory interface, scatter gather technology, a multi-channel DMA, and then 128 and 256-bit AXI. In terms of the library and tools, OpenCV-based imaging vision library, SLAM library, OpenCL, Halide, and OpenVX for the higher level language support, and neural network compiler, OpenVX Glow, and Android neural network API support. DNA. We already mentioned DNA stands for Deep Neural Network Accelerator, and it's a single processor for both vision and AI. And we offer a sparse compute engine, and it's highly scalable. When we take a look at DNA, it's built using two major blocks. One, we call it XNNC Neural Network Engine, XNNE, and other block is our Vision DSP. In XNNE, there is a scalable sparse engine, which is a true random sparse. We offer a true random sparsity processing. And you will see later on that with the use of this true random sparsity, we can achieve a very high MAC utilization. It's also scalable from 256 to 2048, so 2K MAC. It also offers unified frame buffer or unified buffer, and this unified buffer is scalable, where our customers can decide how big this unified frame buffer they would need or they would like. Vision P6 is there. We already talked about it, it's a VLIW SIMD DSP. The main purpose of this is for the future proofing and expanding. So a majority of the network we could run on this XNNE, but in future, a new network comes in, then and some layers or some operations could be offloaded to our Vision DSP. As we spent a lot of time earlier talking about pre and post processing. So this Vision DSP is there to provide support for any pre and post processing. So the same IP can be used for that. And then the same IP could be used to do CV workload. So while the XNNE neural network engine is busy doing some AI workload, the Vision DSP concurrently can be used to do computer vision workload. So in this slide, we are comparing a DNA against competition using Resnet50 FPS. And for simplicity, we have normalized everything to our competitions of 512 Mac at 1, that being 1 for the Resnet50 FPS. On the left-hand side, we are comparing our 512 Mac IP against the competition of 512 Mac IP, and you could see the 512 Mac, our IP can give you 2x performance compared to a competition's 512 Mac. On the right-hand side, we are comparing our 1024 Mac IP, and compared to two competition that we have looked at it, we can offer 2x the performance in terms of FPS, and also even our 512 Mac can offer performance which is higher than competition's 1K Mac performance, and this is due to the Sparse engine that we have. So in this example, on this slide, we are comparing our Cadence DNA performance against Nvidia Xavier. And for comparison purpose, we are using the MobileNet V1 that's used in MLPerf 0.05. And NVIDIA performance are taken from the link that we have provided on this slide. And in order to compare the two IP, we have normalized it to FPS per TOPS. And when we compare FPS per TOPS, our IP can offer 2.4x better compared to the what Xavier, the published data for the MLPerf on this particular network, MobileNet V1. So now if I go back to the typical Vision plus AI workload, you could see that some of the pre-processing can run on Vision P6, the AI workload on XNNE hardware for the DNA, and then even some of the non-convolution can run on XNNE. And the post-processing on Vision P6 can be done like non-NMS or any bilinear interpolation, deblurring, HDR. And there are a lot of networks that will have greater than 10% cycle required for the post-processing. So you could see the pre-processing, post-processing, and the typical AI workload all can run on our DNA IP. So till now, I've been focusing on our hardware IP solution. We spent some time talking about the AI software portfolio. We offer XNNC Neural Network Compiler, XNNC, for our Vision DSP and our DNA product. This XNNC is based on GLOW. It has a native ONNX support, and then we also support TF, CAFE, CAFE2, and PyTorch. For our customers who are using our IP in Android neural network environment, we offer the Android neural network API for all our IP. And for our HiFi DSP, we have HiFi neural network library, ANN library, and we support TF Lite Micro. Now, there are some customers who, for various reasons, they have decided to do their own custom AI accelerator. But then, as we talked about, for the pre and post processing or for the future proofing, they are using our Vision DSP next to their AI accelerator. And for those people, we also offer something called XNNC-Link, and we'll talk a little bit more in the next slide. So as we spent 2 minutes in the previous slide, that we offer XNNC Neural Network Compiler that works through ONNX and GLOW, and it works with our Vision DSP, our both the Vision P6 and Q7 and DNA 150. But then those customers who has their own custom AI accelerator and they are using our Vision P6 or Q7 along with their AI accelerator to develop their own AI solution, they can use our XNNC compiler to generate the code for the neural network that they are targeting, and then use XNNC-Link API to offload the certain layers, whatever the hardware acceleration they have added. It could be convolution only, it could be anything that they have added on it, and then you can offload those layers on the accelerator and run the rest of the layers on the Vision DSP. And by using our XNNC and XNNC-Link, they can reduce the time to market and generate code for their solution very quickly. So as I said earlier, that we've been in the business of shipping the AI IP for a long time, and so we have various customers who are already shipping in a large volume. MediaTek uses us in their application processor, also in their IoT processor called MediaTek i500. Toshiba has used us for their automotive processor. Neuron uses us for their smart camera. And then on the right-hand side, NXP uses our HiFi product for IMX RT600 and Baidu for their Honghu product. So in summary, voice plus AI and vision plus AI for edge requires pre and post processing in addition to neural network processing. In addition to convolutional layers, other layers take considerable cycles. So max acceleration only does not accelerate the AI performance. Combination of hardware acceleration for convolution and programmable DSP provides the best solution for vision the edge AI workload. Cadence Tensilica provides vision AI and voice AI hardware IP with neural network compiler, and we have a large number of customer shipping product using our IP. Thank you very much. I hope you enjoyed the presentation.
Thank you, Pulin. You can go ahead and turn off your screen sharing. And audience members, you can go ahead and submit your questions in the Q&A box. I'll get started. You covered a lot of ground, and that's deserving of how extensive your product offering is. And you guys were one of the first IP vendors to offer some of the IPs specialized for neural network processing. But even though we've talked about it over the years, I think I'm still a little confused on what you see as the difference between processing for AI and processing for computer vision. One of your charts showed, the scalability of the DNA product as far as having more max, but there's more to it than that. Could you go into a little more detail on the differences?
Well, so first, let me answer your question on the vision processing, right? So traditionally, as we enter the vision DSP market, our customers have used our vision DSP to do classical computer vision and image processing. So what are those? You could take a lot of example from the OpenCV type of library, and they could be running a lot of filters like a bilateral filter or Gaussian filters or something like that to do the noise reduction. They may be doing some feature detector application. They may be doing some edge detector applications. So those DSPs are used for classic computer vision and image processing applications, right? So that's how we started. And then what happens is what you see that in AI side, people need to be able to do a lot of processing that is a mix of vision and AI. So then they could use our DSPs to do that, but then what happens that at some point, as I was trying to describe, that our vision DSP can offer you up to one top type of performance. That if you want higher than one top performance, then you could use multiple of our cores, but instead people will use as an AI IP next to it to say, okay, I'm going to offload AI acceleration on our DNA IP. So that's how the differences is between the vision processing versus the AI accelerators.
Yeah. Okay. So it seems like you are supporting a similar kind of architecture as Kavitha talked about for SEMA AI, with one engine that handles the computer vision and one that handles really the convolution-heavy operations. How does that work out for your programming model, for your users?
Well, so that's where our extended neural network compiler comes in the picture, where the extended neural network compiler looks at the AI workload or the network that comes in, and it looks at all the layers and say, okay, where are all the layers going to run? And if we can run most of those on our AI accelerator, then it will run up there. If not, then some of those can end up running on the Vision DSP. And as you know, this is a very evolving market. So new network comes in every day, and not all the layers can be supported in the hardware. So then some of those can run on the DSP, and that's where the whole ability of using the neural network compiler and it figuring out what can I support here on the hardware and what can I support on the programmable DSP is very important for our customers.
Yeah, and I think you made a good point about the need for sensor processing, which I often see when people are just talking about neural network acceleration, that it needs to connect to something, and that something often needs some sort of signal processor, whether it's vision or something else. But is it really two separate skill sets? Do you find that you have a DSP engineer and then you have maybe an AI machine learning engineer? They need to use the same tools. They use different tools, different skill sets.
Yes and no. There is so we as a IP company, we are not developing new networks per se, right? So we are not. We are saying, okay, in order to support this network, what do I need to do on my hardware IP, and what do I need to do in my software tools? So yes, there are different sets of tools sets. The people who know how to program the DSP, people know how to open up the neural network and say, okay, well, how do I take the workload at a different places? So that you need both type of engineers. But what I was trying to say is that there is also the other type of engineer that is saying, okay, how do I make the best neural network to solve problem X, which is not what we are trying to focus. We are saying a problem is solved by our customer. How do I make it so that it will work better on the DSP? How do I make it easy for them so that the code gets generated, so that they don't spend time learning how to program our DSP or our hardware? They are focused on developing new network. We take the network and make it run very quickly, and they can see the results even before the hardware is available with our instruction set simulators, right? So that's what we are focused on. So yes, there is some two level of a skill set, but it's complementary. I guess that's what you could think of.
I think one of the good things is you've got that legacy of Tensilica, and it's very mature, and you have a very comprehensive set of tools that you offer.
That's correct.
We did have a question from the audience then. How do customers normally use your software environment if they wanted to simulate, say, the Vision P6? Do you support FPGA-based prototypes?
Sure. Yeah. So that's a great question. So yeah, so it's you already mentioned that a customer can do instruction set simulator. Customer can also do a system C modeling using the rest of the system if they want to simulate that. And then these are you can synthesize the RTL for any specific FPGA. So I was about to say Xilinx, but maybe AMD, I don't know, whatever happens. But that platform, or the Intel platform, or any other FPGA platform that you're targeting. So we help you, allow any customer to create that. We also have already done some of those design ourselves, so we can provide that. So if customer tells us that I want to bring it up on this FPGA platform, then we may have already done some work where we can provide that to them.
Great. I had a question on one of the things you mentioned as a feature of your IP, is that the true random sparsity.
Yeah.
What does that mean exactly?
So, okay, I mean, everybody know what the sparsity is. You want to, avoid the multiplication with the zero, And so what happens is that every time the inference comes in, there is two things you could do. You can clock gate the zeros, but that saves the power. But versus what we are doing is that we are looking at every inference that coming in. Removing the zeros and multiplying to where the zero is not, and then obviously you have to put back the zero. So it is quite different. It is happening on every inference. It is not just clock gating up the zero. We are removing the zeros, and obviously you have to adjust the data back again, and what it does at the end of the day is it gives you much higher utilizations with the sparse compute engine.
But it's dynamic depending on the data set.
Absolutely, it's dynamic on the data sets, right? So it's happening online, so it's, once the engine is there, then every time the inference comes in, it's working on that.
I had some more questions, but we're at the top of the hour,
Okay.
So we'll have to break here. Thank you, Pulin.
Yeah.
We'll be going to a 10-minute break, which is sponsored by FlexLogix, and so please go ahead and take the break and join us again in 10 minutes for our session on heterogeneous computing. Thanks again, Pulin, and we'll see you later on in the breakout room.
Thank you very much.